Hello everyone. We are talking about PIC18F4550 in details. In today's session, we are going to discuss ADC, which is available on chip of this particular microchip PIC18F4550. So let's start the session, and we will program at the end of or with this video. I will share source code for programming the ADC of PIC184550. Let's start the session. Okay. Objective of this session. Objectives are of this session are to understand the working of ADC converter, how ADC works. Second, we will see to study on chip ADC section of PIC microcontroller PIC18F4550. How many resistors are there, which are used for controlling and data transfer or conversion operation that is carried out on chip of this particular microcontroller. And in the last session we will see the circuit diagram which is used for interfacing 0 to 5 volt analog input with PIC18F4550. Okay, so first, what is ADC? All of you know about ADC in the several subjects you have studied. You have gone through this ADC, analog to digital converter. Okay, in in many subjects, this ADC is included because ADC requires in various applications or in wide applications because we are processing all the data in digital formats. So, for example, if you take computer, telecommunication, everything is digital, mobile phone, everything is digital. So, physical word parameters need to be converted into digital form, that is discrete values, which can be processed by our digital systems. So, for this purpose, for running these applications, okay, these ADCs plays an very important role in the conversion one. So ADC are nothing but analog to digital converters, which converts analog input, which is given to this particular ADC device, that will be converted into digital values or discrete values, or simply in simple words, we can say that these analog quantities will be converted into logic 0 and logic 1. So these digital values we are going to process by using microcontrollers. Okay. In previous devices or microcontroller devices that we have studied, like 8051, there was or there is no any ADC is available on chip. We have to interface external ADC 0804, 0808, etc. for converting these analog values which are fed to microcontroller into digital first. Then we can apply these digital outputs or discrete values to microcontroller so that microcontroller will process these signals and will do further operations which are required for as per the user requirements. Okay, so but if we are talk about PIC18F 4550, PIC18F 4550, so this particular microchip device comes with on chip ADC. Okay, so 10-bit 13 channel analog ADC, analog to digital converter, is available on chip with this particular microcontroller device. Okay, so 13 channels are there and your output, that is digital output, is of 10 bits. So resolution is higher as compared to 8-bit ADCs in the market. There are number of types of ADCs with the bit resolution are available. Okay, so you can see here 8-bit, 10-bit, 12-bit, 16-bit, 32-bit ADCs are available in the market, and that we can use for conversion of analog quantity into these discrete steps. Okay, so you can see these three important parameters which are related to ADC are important to study. First is resolution, second is conversion time, third is reference voltage. Okay, So resolutions are nothing but it is given by bit size. 8-bit ADC has a resolution of 8 bits. That means 8-bit discrete values are given by these ADCs for the analog input voltage. So 256 discrete values, discrete steps we can have for this ADC with 10-bit ADC, which is available on PIC18 microcontroller, has 1024 steps of conversion. 12-bit ADC provides us 4096 steps, and 16-bit provides 65,536 steps after conversion. Okay, so higher is the resolution, your precision is the conversion. Okay, precise conversion this 16-bit ADC will do and will provide very high precise measurement of analog quantity or physical parameters. Okay, so right now we will focus upon 10-bit ADC, which has 1024 bits output, or we can say that 1024 steps of 10-bit is available with our PIC18F4550, which gives us 4.88 millivolt step size. Okay, now what is the step size? It is the smallest change in the output voltage with respect to input voltage, or with respect to any changes in the input or analog quantity. That means what? If we take example of temperature measurement, for every degree change in the temperature, that will change our output by 4.88 millivolt, or steps will be of 4.88 millivolt. Unlike your 8-bit resolution, which is available with not 8, not 4, and not 8 devices, which has 19.53 millivolt step size. So because of bit resolution higher in PIC18 microcontroller, we are getting lower step size measurement for the analog quantities, or conversion for the analog quantities. Okay, so conversion time is nothing but the time taken by ADC device to convert, to acquire analog quantity and convert it into digital form. So total time will be conversion time. Okay, so that we will calculate further. And third is the reference voltage. Reference voltage is again very important because we have ranges of input that we can measure depending on the reference voltage. Okay, if I want to, for example, if I want to measure 0 to 5 volt input voltage, or if I want to convert this 0 to 5 volt analog input voltage into digital form, then I have to connect V reference pins to VDD. Then only I can use this. For lower measurements, we can go for 2.5 reference voltage or 1 volt reference voltage. Okay, so V reference also plays a very important role in this measurement or conversion steps of ADCs. So you can see here, if I connect V reference terminal V reference plus or positive to 5 volt, then I can measure input up to 0 to 5 volt. I can convert my input up to, or which is coming in the range of 0 to 5 volt, which gives us 4.88 millivolt step size. For 2.56 reference voltage, which is applied to or which is connected to ADC, which is available on PIC18 microcontroller, that gives us input conversion range or input measurement range of 0 to 2.56. Okay, for this particular range, step size is of 2.5 millivolts. And if I connect V reference to 1.024 volt, then I will get this particular range 0 to 1 volt, okay, approximately, and my step size will be of 1 volt. Okay, so all of you know that for calculating the discrete values, formula is D out is equal to V in divided by step size. Whatever input we are applying to ADC, analog input voltage, that will get divided by step size to calculate what digital output, which will be a decimal value. Then we can convert it into hexadecimal form. Okay, this is the V reference by your steps to calculate step size. Okay, so 5 volt is the reference voltage and 1024 are the steps. Okay, for the conversion, so 5 volt divided by 1024, it will give, or it gives us 4.88 millivolt step size. Okay, so as we said, as we know, this PIC18F4550 comes with 13 channel 10-bit ADC. So 13 pins are multiplexed, okay, for taking this advantage of analog input channels. Okay, so you can see port A, port E, port B are used as a analog input pins. Okay, or these port pins are multiplexed to have analog input pins. Okay, to analog input function we can apply through these pins. We can use this analog or analog to digital converter by using these pins or through these pins. Any pin we can use for conversion of analog quantity into digital form. Okay, suppose I am going for large application measurement or large application controlling monitoring, okay, in the physical world, then I can connect 13 sensor to this PIC18 microcontroller, and I can convert them into digital form so that microcontroller would be able to process these signals, so that, okay, higher the physical parameters or maximum physical parameters we can monitor and control and analyze for the further application, okay, for the further use. Okay, so you can see channel 0 an0 is having multiplex port pin as a RA0. Okay, it is multiplexed with the analog input. So pin number 2 AN1 is 3. Likewise, 12 number, that is 13 channel. 13th channel will be 33 with port B, that is RB0 is multiplexed as a EN12. It is interrupt pin. Okay, and other functions are given for these particular port pin. So port A, port E, and port B are multiplexed to have analog to input, analog to digital converter pins. Okay, these pin will act as a analog to digital converter pins, and we can configure any one of the pin for one sensor. Okay, so in this way we can connect 13 sensors, 13 sensor outputs to these analog input pins. Okay, so all of you know that it will have multiplexer 13 as to 1. Okay, generally we design 16 as to 1. So here we can say that 13 as to 1 multiplexer is available inside this PIC microcontroller. Okay, that connects 13 channels. Okay, and that converts these 13 channel inputs into digital form. Okay, so you can see AN3 is connected with, is multiplexed with the V reference plus also. Okay, and AN2, that is 4 number pin and 5 number pin, these are connected or related to V reference plus and V reference minus. Here you can connect these pins to either VDD or to required reference voltage, so that required input measurement range can be accessed. Okay, so these are the pin descriptions, and next we will see which resistors are there which are used for controlling the operation of ADC module, okay, which is available on chip of PIC18F4550. So here you can see ADC con 0, AD converter resistor 0, okay, having address of FC2, AD con 1, it is a control resistor. FC1 is the address, AD con 2, okay, it is having address of FC0. Okay, so three control resistors are used for this ADC because we are using 13 channel 10-bit ADC. So our output is of 10 bit, so two resistors are required for this. So here you can see ADC result higher byte and ADC result lower byte. These two resistors are used for storing the result of conversion. Okay, and these ADCON 0, ADCON 1, ADCON 2, these are the control registers. We will see these registers in detail one by one. Let's start. Okay, so first register is ADC control register. It is a special function register of microcontroller PIC18F4550, which is used for controlling the operation of ADC module, which is present inside the PIC18F4550. You can see 8-bit register is there. This is the 8-bit register ADCON 0, okay, which uses only 6 bits of this particular register. Okay, remaining 2 bits, which are higher bits, are unimplemented, or they we can say that these are reserved for the future use by the microchip company. Okay, so let's start with the lower bit first, bit 0. Bit 0 is AD on bit. Okay, so here by writing 1 to this bit, we can enable ADC module. Otherwise, if I write 0 to this particular bit, then ADC module is disabled. Okay, so second is go or done bit. Okay, here you can see ADC conversion status bit. Okay, this is also called as a start of conversion pulse and end of conversion pulse that we have seen in 8051 while interfacing ADC with 8051, that is ADC not 8 not 4 and not 8 not 8. Okay, now these pulses are inbuilt in this particular register. Okay, so here if this particular bit is 1, then ADC conversion is progress, or ADC conversion is going on. That means, okay, if this particular bit is 0, that means ADC has finished its conversion and it is ready to accept next analog input. Okay, and remaining 4 bits are used for selection of channel. Selection of channel, that is channel selection bit 0, channel selection bit 1, channel selection bit 2, channel selection bit 3. These 4 bits are used for selection of channel. If I write 4 zeros for this bit, channel number 1, which is AN0, is selected. If I write 1 1 1 1 to all these 4 bits, then okay, then how what will happen? Channel number 15 should be selected, but we have only 13 channels. Okay, so what bits should be written to these bit values or to these bits? Okay, 1101, that is a 13 channel bit is should be written, okay, to select 13 channel, that is called as a AN12. Okay, so in this way we can write for selection of analog channel select bit. Okay, so this is what ADC con 0, that is the first control register. It is also called special control register, which has address of FC2. Okay, reset values are 0 0. Next is ADC con 1. This particular register belongs to voltage reference and port configuration bits. Okay, so here you can see for this register also 2 bits which are from higher side, D7 and D6, are unused, or they are unimplemented. Okay, so remaining 6 bits which are lower bits are used for selection of particular reference voltage and configuration of port pins. Okay, so here you can see V reference voltage configuration bit, you can see V reference source. If I write this particular bit with one value, then you can see V reference minus is selected. Here if I am using other than 5 volt range, then here V reference negative of that particular supply is connected, V reference negative. And same way VCF0Z0 is configuration bit for V reference positive. If I use 2.56, then I will connect here 2.56 and its negative terminal will be connected to this V reference minus pin. Okay, so here you can as we have discussed, EN3 is multiplexed with V reference function, V reference plus function, and AN2 is multiplexed with V reference negative function or minus function. Okay, so if I want to use 0 to 5 volt range for the input of analog channel, okay, then I should connect these two bits to 0. Okay, that means what, VSS will be considered if I write 0 to this bit, and VDD is considered if I write 0 to this particular bit. So VDD and V, that is 0 to 5 volt range is selected. Here remaining 4 bits are used for ADC port configuration control bits. Okay, these are the configuration of port pins as a analog or as a digital, because we know that all these ports we can use as a digital IO also, that is digital input output also. And here we are in multiplex with port A, port E and port B, so we need to configure these port pins as an analog or digital IO as per the user needs. Okay, so in simple words, if I write all 4 zeros to these port configuration bits, then what will happen? Okay, all the 13 channels will be selected as a analog inputs. Okay, all the analog, all the 13 channels will get enabled. Okay, for these 0000 writing, this port configuration control bits. Okay, this particular bits is written value with 0000. All the 13 channels are enabled as an analog input. Okay, same way if I write 111 to all these 4 bits, then I can use this port pins as a digital IO. Okay, so depending on our need, we can use, okay, any channels as an analog and remaining as a digital IO. Okay, so if I want to use only AN0 as an analog, okay, then what value I should write to this port configuration bits? I should write 1110, because only AN0 is enabled as a analog input and the remaining bits I can use as a digital IO. Okay, so if I want to use this AN4, then I should write this particular value. Okay, so here 1010 I can use for making AN4 analog, and the remaining bits I can use as a digital IO. Okay, now because some port pins are multiplexed to port E, multifunctions with the port E, from the port E, so this port we use for controlling the LCD. So generally we should use these port pins as a digital IO and remaining as a analog input. Okay, so these are the port configuration bits. Okay, for selecting what particular pin as an analog or digital, or to configure particular pin as an analog input or as a digital IO. Okay, so this we can do by writing particular value to ADCON 1 register. So what value we can calculate 00 for 0 to 5 volt signal, and you can see here if I want to this use, then if I want to use this particular all 13 channels as an analog input, then I should write all zeros to this bit. Okay, sorry, all zeros to this bit. So if I write ADCON 1 is equal to 0 cross 0 0, okay, I will use 0 to 5 volt input voltage range, and I will accept 0 to 5 volt as an analog input range. Okay, and I will use all 13 channels as an analog input. Okay, so I can connect 13 sensors to these 13 channels of ADC module of PIC18F4550. Okay, so this is all about ADCON 1. Now last control register is ADCON 2. Okay, here you can see ADFM bit. Okay, this is the last, this is again 8-bit register. Okay, 7 bits are allocated with some function, and one bit is unimplemented. Okay, that is reserved for the future use by the company. Okay, so we will start with the last bit, ADFM. So address result format select bit. Okay, or simply we can say that ADC result format select bit. Okay, if I write 1 to this, then right justified selection, and 0 left justified selection. Okay, what it means we will see in few minutes. Okay, and you can see here acquisition time selection bits are there, ACQT 0, 1, 2. Okay, these three bits are given for acquisition time select bits. Here you can see total conversion time is multiplied with 0. If I write 0, 0, 0 to these three bits, if I write 1, 1, 1, then 20 times acquisition time is selected. That is the conversion time. Okay, so here you can see ADC these acquisition time select bits we can use. Okay, we will discuss again. And last is, just a minute. Here you can see ADC conversion. Remaining three bits are given for ADC conversion clock select bits. Here we are going to use FOC as a clock signal for ADC conversion or ADC module. Otherwise, on chip oscillator which is available in PIC18 microcontroller, that can be used as a clock source for ADC module. Okay, let's see what functions are available with this, what options are available with this. Sorry, options are, if I write 000 to these three bits, I will select FOC by 2. If 20 megahertz crystal is connected to this particular PIC microcontroller, then I will use 10 megahertz for ADC conversion. If I go for 100, then FOC by 4, 5 megahertz. If I go for 001, then I will use FOC by 8. Likewise, you can go up to FOC by 64. This much minimum conversion time I can select for the conversion of analog input quantities into digital form. If I go for these two options, then I will use on chip RC oscillator that is available on chip of PIC18 microcontroller. Okay, so if I go for this, then I have to use RC components to run that particular oscillator. Okay, so this is all about ADCON 2 resistor. It is related with the acquisition time and conversion time. Okay, so next is ADFM bit. Here, if ADC result format select bit is written with one value, then the right justified selection mode was there. So that what it means, we have 10-bit ADC conversion bits, that is the output bits are 10 bits, so we require 2 bits, 2 registers to store the output or conversion result. Okay, so right justified, that is ADC result lower byte and ADC result higher byte, these two registers are used for storing the result of ADC conversion. So if I select right justified, then lower 8 bits of the result will be stored in ADC result lower byte, and remaining 2 bits, that is higher bits, will be stored in ADC result higher byte. Okay, so this register used to store higher 2 bits, okay, of the 10-bit result. Okay, and lower 8 bits are stored in lower byte. Exactly opposite will happen if I write ADFM bit is equal to 0, then left justified mode will be selected. So exactly opposite will happen. Okay, lower 8 bits will be stored in ADC result higher byte, and remaining 2 bits will be stored in ADC result lower byte. So as per the user need or our need, okay, we can select right justified mode or left justified mode. Okay, here you can see the select circuit diagram or internal block diagram of ADC. You can see multiplexer is there, so 13:1 analog multiplexer is there, and selection pins are there. So CHS0 to CHS3, these are the four selection bits or pins which are used for selecting these 13 channels. Okay, and these channels are connected with the V reference plus minus as well as VDD and VSS, that is the ground. Here voltage configuration bits or V reference configuration bits we can use for giving the reference voltage to ADC. Okay, and the result will be stored in ADC result higher byte and lower byte. If right justified format is selected, then 8 bits will be stored in the lower byte register and higher 2 bits, remaining 2 bits will be stored in the higher byte register, ADC result higher byte. Okay, if left justified selection mode is applied, then 8 bits will be stored in the address or ADC result higher byte, and remaining 2 bits will be stored in ADC result lower byte. Okay, these two registers will hold the conversion results of 10 bits. Okay, now here how ADC is operated. Okay, that very important steps, or because through this we are going to write program for ADC module. Okay, to run this ADC to convert physical world quantities into analog into digital form. Okay, so these steps we need to follow to configure or to run this ADC module which is available inside the PIC microcontroller. First step is configure the ADC module. Okay, configure the analog pins, voltage reference and digital IO pins, ADCON 1. Okay, select ADC channel, that is we can use through ADC con 0. Select acquisition time and conversion time by using ADCON 2 resistor. Okay, and turn on the ADC module. After configuring all these things, we can turn on ADC module. Okay, now here in two ways we can do this operation. We can either generate interrupt, okay, or we can wait for go or done bit. Okay, in this two way we can take a result of ADC. We can operate this ADC in two ways. Okay, one interrupt is given for ADC. Okay, that ADC interrupt flag. Okay, that is used for generating the interrupt. Whenever ADC finishes its conversion, this ADIF bit will be set to 1 to indicate that ADC has converted its analog quantity into digital form and it has generated interrupt. So this ADIF flag will be raised to 1. Now to allow this interrupt, we need to set these particular bits: ADC interrupt enable bit and global interrupt enable bit. These two bits should be used in a set mode. Okay, we should write logic 1 to these two bits, then only we can use this ADIF interrupt flag or ADC interrupt. Okay, this particular thing is used if we required an interrupt, okay, in the system. Next, here we will apply some delay, okay, in the program for acquisition time. Okay, it is also if required. Okay, then we will write logic 1 to this particular bit go or done bar bit from ADCON 0 register. Okay, if I write 1, then ADC will start its conversion and we will wait for this particular thing. Okay, ADC will finish its conversion and it will give logic 0 signal on this particular bit. Okay, so here we will wait for ADC to complete by either polling method go or done bit to be cleared. Okay, so whenever ADC finishes its conversion, this bit is cleared automatically by the microcontroller, or we will wait for this particular flag, ADIF flag, ADC interrupt flag. This will be raised to 1. Okay, then we can say that ADC conversion is finished. Okay, so after this we will read the result of ADC, which is stored in ADC result higher byte and lower byte register. Okay, if interrupt is generated, then after taking the result from these two registers, one should clear this ADIF flag to go for next operation, or to go for next conversion. Okay, so here ADIF flag will be cleared. Okay, and we will follow the step 1 2, or we will go for these steps to have continuous conversion mode of microcontroller or ADC. Okay, so these are the steps that one should follow for ADC operation, or for running the ADC module of PIC18F4550. Okay, here you can see the circuit diagram, which can be used for interfacing 0 to 5 volt signal to this particular RA1. AN1 here we have selected, okay, for this particular circuit diagram. So you can apply 0 to 5 volt signal. You can use this to RA1, AN1. So here output will be displayed on LCD panel, and port E is used as a control port, and port D is used as a data port. Okay, so this is a simple connection that we required for on-chip ADC programming. Okay, and these are the minimum connection diagram or minimum connection requirements. Okay, one is crystal and second is reset circuit. Okay, these are required for minimum configuration or minimum connection diagram, or as a minimum connection diagram. Here frequency is considered as a 20 megahertz. Okay, so 0 to 5 volt signal is applied. These all are fixed: crystal, reset, okay, LCD, and this data port and control port of LCD. These connections you should remember in every circuit diagram, and you should use all other pins for giving analog input, for connecting keypad, for doing DC motor functioning. All these you can do this through this. Okay, so this minimum connections we should remember all time. Okay, while writing papers, students are making very mistakes, silly mistakes while drawing these circuit diagrams. Okay, so you should remember, you should study well. Okay, you will get maximum marks. Okay, so these are the some calculations that we will see. Okay, for 20 megahertz crystal, here you can see 20 megahertz is converted into time, 50 nanosecond is the time. ADC clock source, here if we select FOC by 64 by putting this into this particular ADC conversion clock bits, here you can see 110 is written. Okay, for these bits FOC by 64 is selected, so here 110 is written. So ADC conversion time is 64 into TOSC, so total time is 3.2 microsecond. Okay, typical time required for conversion is minimum zero point 0.7 microsecond. Okay, so it is higher if I select FOC by 64. Okay, then typical conversion time is calculated by using this formula that is fixed: 11 into TAD. So 11 into 3.2 microsecond is equal to 35.2 microseconds. Okay, and here you can see acquisition time is selected in mode with twice of TAD. Okay, so this is the acquisition time. This much time is required for acquiring the analog input signal. Okay, 6.4 microsecond. So 2.4 microsecond, 6.4 microsecond is greater than this typical value, and you can this add these two values to have what effective conversion time, that is the total time which is required for ADC module to convert your analog quantity into digital form. Okay, so typical conversion time, 11 to TAD, that is 7.7 microsecond. This is the typical time TAD, and into 11. Okay, that is the typical time, and we have a higher value. so that we can use this 10-bit ADC for analog to digital conversion. Okay, so these are the this this is all about ADC module in PIC18F4550. Okay, we can write program through it. Okay, so thank you very much. Okay, goodbye.